Now, our next paper first came up as we were looking at the theory papers, and so it doubles as our exemplary track paper from theory, and then it's written by a student, so it is also our best student paper. This is Giacomo Lanzani, Dynamic Concern for Misspecification.
Thank you very much. Thank you very much. I'm extremely grateful to have the opportunity to present my work here, and let me join Raul in saying thank you to the organizer for the amazing work that they did with this conference. So, the paper that I'm going to present is Dynamic Concern for Misspecification, and let me try to give a little bit of motivation to this broad audience. Misspecification, in the sense of belief of the agent that don't include the true data generating process as a possibility, are a pervasive problem in economic setting. And this is true from the case of very sophisticated agents to the case of more naive agents. For sophisticated agents, think about central banks. Central banks use models to assess the impact of the inflation, the direction on inflation and unemployment. And of course, these models are useful to make decisions, but none of them is a complete description of the reality. All of them are incomplete and to some extent are misspecified. And at the other extreme of the spectrum, you have agents in a social network, maybe on a social media, that may have difficult time in understanding the amount of redundancy in the information that they receive from two different sources. I receive the same similar signal from two different people. I may not know whether it's a repetition of the same signal or two genuinely different pieces of information. And misspecification is even more a problem in situations that are sort of more novel, like the problem related to climate change for a regulatory body, where we just don't have a long sequence of empirical observation about this level of human action. And so we build models that are informed from physics and biology, but of course these models have a high likelihood of being misspecified. Now, what is the economist's approach to this kind of problem? Well, we like the Bayesian benchmark, and therefore there has been a fast-growing literature started by the contribution of Esponda Puzo in 2016 about what happens when agents are misspecified and learn about the environment in a Bayesian way. So they posit a set of models, they learn about them in a Bayesian fashion, but they are misspecified about. Now, the main contribution of this literature has been to unify, provide a unifying explanation of different behavioral biases in terms of this misspecified learning. And there I provide a list of these kind of biases that have been explained. However, this literature had, in my view, one main limitation. It always assumed that the agent ignores the possibility of being misspecified, that the agent is has complete trust in their model. And this is, both from a normative and descriptive perspective, somewhat unsatisfactory. From a normative point of view, this same literature emphasized that misspecification can create a lot of performance loss in the long run. So by ignoring this possibility, the agents are exposing themselves to severe performance loss. And from a descriptive point of view, we know that many models of decision theory that involve uncertainty or ambiguity aversion can be interpreted as a way to hedge against the misspecification of your model. And by now, we have evidence that agents tend to display this sort of ambiguity or uncertainty aversion in many settings, so probably it is not the case that they completely trust their model in these learning problems. So that's the sort of state of the literature and main problem with the literature. So what is my approach to try to overcome this problem? Well, I propose a model of agents who have three main features. The first one, I think, is the one that is most familiar to this audience, is an agent who is learning about the environment through the consequences of the action that they are playing. The second is one key departure from the literature so far, in that I let the agent be concerned about the possibility of being misspecified. And I do this by incorporating some preferences that allow for concern for misspecification that has been widely used both in the engineering literature and within economics, in the macroeconomics literature, and in particular in the form of the robust control preference of Hansen and Sargent. And third, and this is sort of probably the main innovation of the paper, I let the level of concern for misspecification to depend on the data. So the loose idea is that we expect that if an agent observes a long sequence of observation that is perfectly consistent with their model, they are going to decrease the level of concern for misspecification. While if observe something that is hardly rationalizable by any of their model, they are going to raise the level of concern for misspecification. Okay, so these are the three key ingredients of the setting that I study. What are the flavor of the result before jumping into the model? Well, the first result is a normative result. It's a result about what is a good way to adjust the level of concern for misspecification in repeated decision problem. And it's going to single out essentially a unique, statistically sophisticated way to adjust the level of concern for misspecification that guarantees two desirable properties. That the agent always obtain their min-max payoff, and that if the agent is correctly specified, is going to achieve no regret in the long run. Then I build on this normative result to provide a descriptive result of the long-run behavior of a decision maker when they either follow this statistical benchmark or depart from it in the direction of being excessively demanding in the evaluation of their model or excessively lenient in the evaluation of the performance of the model in explaining the data. Then there is a second theoretical result in which I show that the existence of an endogenous concern for misspecification naturally induces in some environment cycles in behavior, and I characterize the long-run frequency of action when this cycle appears. And of course, the paper has also application to misperception of the tax schedules that I think I'm going to sketch today, and to cyclical monetary policies that are a little bit farther away from this audience, so won't be in today's presentation. Okay, so this has been a very high level, so let me give a little bit more concrete setting and describe what is the situation that I'm analyzing. I'm looking to an agent who is repeatedly choosing from a finite number of actions A in A. So there are consequences Y and Y, and the agent has a utility index that takes as input the action and the consequence and returns a level of satisfaction, depending on the two of them. So each action A induces a probability distribution over consequence. So by playing action A, there is an objective probability distribution over consequence that is induced. The agent knows the structure of the problem in that they know that the environment is such that the action that I'm taking today is the only thing determining the outcome, but they don't know the true data generating process. So they don't know this collection of action-dependent probability distribution over consequence. And they deal with this uncertainty in a quasi-Bayesian way. Let me just emphasize before describing this quasi-Bayesian way that one of the most standard case that is covered by this setting is the one of subjective bandit problem. But this framework is in general more, in principle, more general. Now, what is the benchmark way that in economics we use to deal with this kind of problem? Well, we assume a completely Bayesian agent who formulate a set of possible data generating processes. In this case, suppose that they are indexed by parameters. And each of these data generating processes of this parameter describes a set of action-dependent probability distribution over consequence. This is exactly the counterpart of the true data generating process. So it's a set of action-dependent probability distribution over consequence. Now, the agent is correctly specified if one of the models that is envisioning coincides with the true one. But in general, we care about the case in this working case about misspecified agent. Now, what is the optimal behavior for such a Bayesian subjective expected utility maximizer? Let me focus on the case of a myopic decision maker for today's talk. In that case, the subjective expected utility maximizer will perform a two-level expectation maximization. So they look at the expectation with respect to their belief over the set of parameters, and for each of these parameters, we look at the maximization of the expected utility. So that's the subjective expected utility benchmark. However, we want to allow for the idea that the agent have an incomplete trust in their model. And to do so, I need to introduce two pieces of notation. Let me denote by lambda the level of concern for misspecification, a real number that is going to represent the level of concern for misspecification of the agent. And for every 2 distribution, denote as P prime the relative entropy between these 2 distributions. Now, a decision criteria that has been proposed in the literature by Hansen and Sargent and slightly generalized in recent contribution is this average robust control evaluation. So it's important to get this decision criteria because it's something that is going to be driving the result. So the decision maker evaluates each action, again, with a 2-step procedure. And the first step is exactly equal to the previous one, the average over the possible data generating process. But they realize that each of the data generating process that they are considering may be misspecified. And therefore, they don't compute an expected utility maximization inside the integral, but they take a constrained worst case scenario approach, in which they minimize the expected utility over all possible probability distribution, but they get a utility bump by moving away from the conjecture model. So it's worst case scenario, but worst case scenario that cannot be too far away from the distribution that you are conjecturing. And the lambda is exactly what is sort of governing this trade-off between robustness and the fact that you trust a little bit, at least a little bit your model. And the Hansen and Sargent 2001 robust control model is the case in which there is a single model that you are considering. So mu is a Dirac measure on a single theta star. Now, this is a criteria that accounts for robustness to misspecification, but describes how the decision maker is going to behave for a given belief and level of concern for misspecification, while we want the preference to adapt to the received information. And in particular, since we have a Bayesian component, the belief, I'm going to stick to Bayesian updating for the evolution of the beliefs. But I'm going to let the concern for misspecification be a function of the data observed so far. And first result is that there is a critical relation between the level of concern for misspecification of the agent and the likelihood ratio test of their model. Let me explain why. Well, as I said, the first thing that we want to do is we are allowing for a level of concern for misspecification that is data dependent. What is a good way to adjust this level of concern for misspecification? Let me give you 2 desiderata that we may have across this problem. The first one is safety. So something that we could require to the decision maker is that they are always able to achieve a payoff that is equal to their outside option. So I have an outside option in this problem, something that guarantees some payoff no matter what. Then the long-run payoff that I should obtain should not be smaller than this safe guarantee. So this is a very minimal requirement, especially compared to what we impose in learning problem in computer science and economics. A second requirement that you can pair with that is no regret under correct specification, in that if the agent is indeed correctly specified, in the long run they achieve no regret. So maybe with a suboptimal speed, but there is no regret in the long run that if the agent is not misspecified. And these 2 conditions are relatively mild, but in this setting, they single out a essentially unique way to adjust the level of concern for misspecification. And this is going to be the first theoretical result of the paper, that one way to achieve safety and consistency across all possible decision problems is to keep the level of concern for misspecification proportional to the likelihood ratio test of your model, with sufficient responsiveness to the likelihood ratio test of your model, the average likelihood ratio test, so you have to normalize over period. And these allow you to obtain safety and no regret over all decision problems. And there is also a partial converse in the sense that if the level of concern for misspecification of the agent grows either asymptotically faster or asymptotically slower than this likelihood ratio test statistic approach, safety or no regret under correct specification are going to be failed in some decision problem. And these allow me to define a taxonomy for the decision maker in terms of a statistically sophisticated type, that is one that keeps the level of concern for misspecification proportional to the likelihood ratio test of their model, a demanding type for which the level of concern for misspecification grows at a faster rate than the likelihood ratio test. So that's the idea that you become very quickly disappointed by the performance of your model in the unexplained evidence in your model, and a lenient type that has a level of concern for misspecification that grows at a slower rate than this likelihood ratio test approach. And this captures the idea that you attribute too much of the unexplained evidence to sampling variability. Why I'm considering these three cases? Because it's good to know what works normatively. In economics, we often have the descriptive approach, and there is, for example, some evidence in favor of agents being of the demanding type. This is what is called the belief in the low small number in behavioral economics literature. So I have three different possibilities in terms of how the agent is going to evaluate the performance of their model. They are going to relate with three different long-run outcomes in terms of behavior. So in economics, we like to describe the long-run behavior of the decision maker in terms of equilibrium condition, in terms of stability property between the action and the belief of the decision maker. And for this kind of problem, it will turn out that three possible equilibrium concepts, depending on the attitudes toward model failures, are going to play a key role. The first, before defining the free equilibrium notion, let me denote as theta A the set of parameters that minimize the relative entropy from the two data generating process when action A is played. So they are the QA theta that are closer to the true distribution PA star. Now, with this, I can give you the three relevant equilibrium concept. The first one is the concept of Berk-Nash equilibrium. This is the workhorse equilibrium concept of this literature on Bayesian misspecified learning. And it requires the following fixed point condition. The action must be a best reply, a subjective expected utility best reply to beliefs that are supported over only the best fitting model. So action that are best reply to the best fitting models. Best fitting models given that that action is played. Then a second equilibrium concept is max-min equilibrium. This is a very worst-case scenario approach in which the action must be a max-min best reply to all the distributions that are minimally consistent in the sense of being absolutely continuous with respect to some of the models conjectured by the decision maker. And third, zero-bust equilibrium. So zero-bust equilibrium is a novel equilibrium concept that is very related to Berk-Nash equilibrium, but is different for a key aspect. The action is required to be a best reply to some level of concern for misspecification and some belief. And again, the belief must be consistent with the evidence in the sense of being supported over the best fitting models. But now, the level of concern for misspecification is endogenously determined as proportional to the relative entropy between the true data generating process and your best explanation of the data generating process at the equilibrium action. So this endogenously determines the level of concern for misspecification. So free equilibrium concept, previous normative benchmark, we get the main descriptive result of the paper. Depending on how the agent behave with respect of their model evaluation and the normative benchmark established before, they are going to concentrate their behavior on these three different equilibrium concepts defined in the previous slide. So in particular, here, for this result, I'm looking to the possible limit action. So to what action can arise as the limit behavior of the decision maker. And the conclusion is that if the agent is excessively lenient in the evaluation of your model, you recover the standard result in this literature on misspecified Bayesian learning. The limit behavior must be a Berk-Nash equilibrium. But that's the case only for an agent who is excessively lenient in the evaluation of the model. If the agent is excessively demanding in the evaluation of the model, then the limit action must be a max-min equilibrium. Whereas if the agent is statistically sophisticated, then you recover this zero-bust equilibrium, so preference non-degenerate preference, Hansen and Sargent. So taking stock, this is providing a learning foundation with different decision criteria that has been widely used in decision theory and studied there, as a consequence of an inability to explain the consequence that you have observed so far, combined with different attitudes toward this failure in explaining the data. It predicts that there is a positive correlation between being misspecified and being ambiguity or uncertainty averse, and there is a causal relation in this, in the direction of misspecification inducing more uncertainty or ambiguity aversion. And there is also possible stochasticity or path dependence of the equilibrium of the long-run ambiguity aversion. Now, let me give you an example to make things a little bit more concrete that has been studied with misspecified learning. So one setting that has been extensively analyzed is the one of misperception of task schedule. So there is an agent who is choosing a level of effort A in A at some cost. And they are facing a convex task schedule, T. And it has been empirically reported that around 40% of US taxpayers feature this, representative sample of US taxpayers, features this scheduling bias that simplifies a progressive tax schedule into a linear tax schedule. So they sort of fit a linear model over this progressive tax schedule. And with this simplification of the tax schedule, in which you try to estimate a linear tax schedule from a progressive tax schedule, the natural conclusion is that the agent ends up underestimating the marginal tax rate. So I'm fitting a linear function over a convex function. What I end up doing is computing an average tax rate that is the average over all the levels of income up to my final income, and this is obviously lower than the real marginal tax rate that I'm facing. And so the prediction of the misspecified learning in this setting is an excess of effort, underestimation of marginal tax rate and excess effort supply. However, this is only partially consistent with the data, in the sense that in this data, you observe that a lot of agents end up indeed underestimating the marginal tax rate, but when you look at their behavior rather than their belief, is not shielded that much in the direction of excess labor supply. And this is inconsistent with this misspecified learning explanation with Bayesian subjective expected utility maximizer, but is exactly what is predicted by an endogenous concern for misspecification, in that the agents who are simplifying the tax schedule are aware that, I'm fitting the linear tax schedule, so if I have to give you an estimate, that is going to be the estimate, but I don't trust my estimate completely, and so I don't want to expose myself even more to a tax schedule that I'm not understanding. So it's rationalized much better the data from this setting. And with the last 2 minutes, let me just very quickly discuss a theme that I haven't highlighted so far. There are natural settings in which zero-bust equilibria may not exist, and the key intuition can be given in a setting with 2 actions. So it may be the case that an action is a best reply to a high level of concern for misspecification, but when played, the consequences that I obtain are very well explained by my model. And in that case, I'm going to lower the concern for misspecification while I'm playing that action until a moment in which I want to switch to the other action. The other action has consequences that are poorly explained by my model, so I'm going to raise gradually the level of concern for misspecification playing the action and switch back to the previous action. And a theoretical result that I'm not going to describe in detail is that if in that case you can go to a mixed equilibrium concept and show that it characterizes the empirical frequency of action when the behavior does not converge. So I'm running out of time, so let me conclude. What I do in this work is to propose a way to model an endogenous misspecification concern, and first of all establish a normative benchmark. And then I look descriptively at what are the possible limit action for agents that depart from this normative benchmark in the direction of being more demanding, more lenient, or following the benchmark. And I show that an endogenous misspecification concern naturally induces cycle and behavior and characterize the limit empirical frequency of action in that case. Okay, thank you very much. I hope
So once more, we'll take one question. Okay, I'll ask the question again. I was sure, I'll ask the question instead. I was sure when you gave the three types, sophisticated, lenient, demanding, and then the three economic consequences, if there was any justice in the world, Burke-Nash would come out of the sophisticated agent. And so I was surprised to see it's the lenient one that gives Burke-Nash.
Yes, the one part of sophistication that is associated with the Burke-Nash is the fact that the beliefs are going to concentrate over the best explanation. So this calls for sophistication. But in this is also what is supported by the robust equilibrium. So that part of good behavior in terms of statistics is maintained by sophistication. The lenient one behaves well in terms of estimation of the parameters, but naively ignores the error term. So the robust equilibrium with respect to Burke-Nash equilibrium is more sophisticated in that it estimates well and take into account the error term in the estimation. So that's the way in which is more sophisticated than Burke-Nash.
Okay, I want to thank Giacomo and Rahul for great talks, for letting me squeeze their talks a little bit and adjusting on the fly to get us closer back to schedule. And I thank you for being patient and for being a great audience.